And the chat hear me okay? Okay, so as usual, don't forget to do the seating survey, section 3, ILC 118. Upcoming due dates. Homework 5, originally due last Friday, is due this Friday at 5. There is a full revised homework midterm and an activity schedule posted on Piazza. This is the short version of it. It turned out that there were 2 homeworks at the end of the semester that were really short compared to the rest of the semester, so I simply combined those 2 weeks and everything shifted down by 1 week. That does adjust the 2 midterm exam dates a little bit. I'm still trying to figure out the best way to handle the 4th midterm and the final so that it's not too overwhelming right at the end. I will, once I have that figured out, I'll let everybody know about it. And the new activity due dates are listed here. So the next one is going to become available for next week, and then will be due the following Tuesday on that. If any of these shifts in dates ends up being a burden to someone because they'd planned on it being at one particular time instead of what's listed here, please let me know, and I will find some way to make sure that it doesn't end up being a burden for you. This week, because so much has gotten moved off, there are a few things that are added in that's sort of part of this class reset that we're doing. There are 3 videos I want to make sure you watch: the exam walkthrough, the frequently raised objections video, and the grade projection spreadsheet video, which also explains the new grading scale. So make sure you go in and do those, please, this week. Additionally, there is a form on Blackboard for exam regrades. The intent of this is to be able to get you points in places where a later question depended on a prior question, and if you did the later question right from the wrong information from a mistake on the first question, I want you to be able to get points for that. And this form is intended to give you a mechanism to do it. I've identified which questions qualify in that regard. You select which of them you actually did correctly, and I will go back in and regrade those. Be certain to read the instructions carefully, because the way this is working is set up so that I don't have everyone sending me a request to regrade every question, because that would just be absolutely impossible to do. So read the instructions very carefully. And this is due on Friday, and so that should give you time to go through the exam walkthrough video, make sure that you know what you're doing with it, and then we will, and then if there are questions about any of them before submitting your exam regrade request, then we have time to address those either through office hours or Piazza or whatever. Okay, any logistical questions before we start getting into the kinetics content for this week's, the homework that's due on Friday? What time on Friday? Yes, 5 o'clock. I figure since things are already due at 5 o'clock, I shouldn't be making something new not due at 5 o'clock so that people don't get confused about that. Anything else? Yes. Yes, absolutely. So when homeworks get moved back, anything that's associated with that homework is also getting pushed back as well. So I have a couple of videos that I'm almost ready to post, and I will have more later this week for next week's material. Yes. Okay, let's go to some kinetic stuff. So these there are quite a few of them, which I think is excellent. I'm thrilled that people are giving me so many questions to work on. And I've tried to group them so that we can sort of be in a topic area for a little bit as we go through. The first set is about reaction rates, and then what are they? How do we use them? What do we mean by an instantaneous rate? How do we compare rates of different species? and then a solvent issue. So let's talk about these quite a bit. So the general idea of a reaction rate is that we know that some reactions happens quickly. If you imagine lighting a match, that happens quite quickly. If you imagine there are other rates such as graphite that has, or charcoal that is being compressed underground, turning into a diamond, that is a very slow kind of process. And so what we want to do is have some way to quantify that idea, to take it from just, oh, it's fast or oh, it's slow, into something that is quantitative so that we can do something with it. And the way we do that is by looking at the concentration of either reactants or products. Now, remember that this square bracket notation is used for concentration of a species in units of molarity. Okay, so whenever we talk about a rate of something, that means change with respect to time. So if you think about position, then we would have a change in position with respect to time. Or if we look at the instantaneous versions, and I'll talk about the difference of that in a minute, we would talk about the derivative of position with respect to time, and we call that in physics a velocity. We are doing exactly the same concept for reaction rates, concentrations, and we are looking at a change in concentration with respect to time, or I shouldn't say this equals, but is equivalent to the derivative of the concentration with respect to time. And if we, with this idea of a speed, with this idea of a reaction rate, if we plot on a graph what the concentration of a species, let's consider it to be a reactant, with respect to time is, we will frequently see something that looks like this. So what this is saying is that here, the reaction is changing the concentration is changing pretty quickly, and so it's happening rapidly here. Down in this region, it is not changing nearly as quickly, and so the reaction has slowed down by the time it gets here. Very frequently, this is because by this point, there's not much reactant left, and so the actual change in the concentration you're going to have is not going to be very fast because there's not much to begin with. Okay? But up here, when you have a lot of it, it's going to be happening quite a bit. So that's the general idea of what we mean by a reaction rate, is this change with respect to time. Now, there is the non-calculus way to do this, and there's the calculus way to do this. The non-calculus way to do it would be to say, what is the concentration at time 1? What is the concentration at time 2? And we will do the change as just delta concentration over delta time, right? That's the non-calculus way to do it. The calculus way to do it is to say, well, that is missing this whole curve that's between those 2 points. It's assuming that it's a straight line. And so what you do is you take the instantaneous slope at a point right here, and that is the derivative of concentration with respect to time. So the derivative version is much more precise in terms of talking about concentration rates. What is that annoying whine? It's nothing associated with this stuff. Oh well. All right. So that's the general idea of what a reaction rate is, and that's the idea of what an instantaneous reaction rate is, that it is the derivative version rather than the delta version. Okay. The next aspect of it is clearly this is going to depend on which species we're looking at. If we have some kind of reaction that has multiple species, maybe it's A plus B goes to 2C. Let's say A plus 2B goes to 2C, something like that. Then we could have A look like this. We could have B look like this. And we would have C look like that. So, but if we're talking about this all happening as part of the same reaction, then we need to have some way to take these different changes in concentration with respect to time and figure out how we can talk about the rate of the reaction rather than the rates of the individual components. There has to be some kind of connection between them. And that connection has to come from the stoichiometry. So if this is our reaction, then for every molecule of A that reacts away, how many molecules of B react away? Correct, 2. For every molecule of A that reacts away, how many molecules of C are produced? 2, just straight from the stoichiometry. So this means that there is something that has to be true, that if we take the change in concentration of B with respect to time and compare it to the change in concentration of A with respect to time, then this is happening twice as fast as this. So we need to multiply it by 1/2 in order to get the rates be equivalent. This one is going to be the same as this one, but it's being produced instead of reacted away. So we need to have this one be negative 1/2 dC dt. So that all of these can be a rate. So what we mean by the rate R is that it is the rate of the reaction as written. So anything with a stoichiometry of 1, with a stoichiometric coefficient of 1, that is a direct measure of the rate. Anything with a different stoichiometric coefficient than 1, you have to divide the rate of the change of that species by your stoichiometric coefficient to get back to how fast does the reaction happen. Okay. And you have to use negatives for the product, excuse me, negatives. I did this backwards, didn't I? Let's try this again. That's positive, these are negative. Because we want the rate to be defined as positive when the reaction is going forward, so that the production of C, our dC dt is positive because it is going up. The reaction rate is going that direction. We want that to be positive, so this sign is correct, and it is the reactant concentrations that we have the negative sign in front of, because those concentrations are going down. They will have a negative slope, and we want the reaction to be a positive number, the reaction rate. Okay. Any clarifying questions on this idea of either what a reaction rate is or how we relate them to each other within a given reaction using the stoichiometric coefficients? No. Okay, good. So what this means then is that we can tackle problems like this one just using the information we have so far. We don't even have to get to the what the rate law looks like in order to answer this kind of question. So we want to know the formation of H2O by starting with the consumption rate of O2 and figure out what the relationship is. So let's write our rate in terms of these two. So O2 is a reactant, so it needs to be negative. Our coefficient is 5, so we do 1/5 d concentration O2 dt. Now let's look at the H2O. That is a product, so it's going to be positive. The stoichiometric coefficient is 6. So d concentration H2O dt, that because each of these equal the rate, they have to equal each other. And so now we want to know, what do we multiply this by to get this? So what we're doing now is solving for this. So we multiply through by 6 to have -6/5 dO2 dt equals dH2O dt. And we find that the answer is we multiply the rate of consumption of O2 by -6/5 to get the rate of production of H2O. Yes?
So how come we don't have to look at the NO in the equation?
Don't have to look at what in the equation? The NO or the NH4? Well, it is also true that the rate equals some other things. It is also true that this equals 1/4 the rate of rate of production of NO dt, and it also equals -1/4 NH3 dt. So all of that is true, but that's not what the question is asking for. The question is asking for what is the rate of consumption of H2, excuse me, what is the rate of formation of H2O given the rate of consumption of O2. So all 4 of these things are equal to each other, but only 2 of them relate to what the question's asking, so we just look at those 2. Okay. Any other clarifying questions on this concept? Okay. So if the solvent is part of the reaction, why don't we use it in the reaction rate? So this is, in this case, where are we? Okay, let's actually look at this specific reaction right here in trying to answer that. Now, this reaction is probably, based on the fact that there's O2 and NO involved, this is probably happening in the gas phase, right? So these are probably concentrations in the sense of moles of gas over the volume of the gas rather than in terms of it being dissolved in some kind of solvent. But if this were happening in solution, then we would label this as aqueous, we would label this as aqueous, we would label this as aqueous, and we would label this as liquid because it's the solvent, okay? It's not a solution of water in water, right? And then if you think about what is happening to the concentration of H2O in this case, you're starting off with with something that is almost pure water as the solvent. The concentration of water is, I'm trying to remember now, I think it's something like 50 molar, if I'm remembering correctly. If you take the, we could figure that out, but it would be kind of a sidetrack. What's the concentration of water in water when it's pure water? You take the number of moles in water in 1 liter, divide it by 1 liter, and you get that value. And it's a big number. It's something like 50. And usually you're dealing with concentrations of any solutes that's 1 molar or less typically. And so whatever reaction's happening, your 50 molar is not changing very much over the course of the reaction because it's still going to be the very, very close to 50 molar. And so typically in that case, so while yes, there is water being produced, it's not something that's experimentally very useful to talk about because we can't very easily go in and take a sample and say, what's the concentration of water right now? What's the concentration of water later? It changed over in a decimal place somewhere, but not very much. So that's why we don't tend to talk about the rates of reaction of the solvent, because it just doesn't change. Okay, so all of that discussion here was before we even got to the idea of a rate law. When we do get to the point of a rate law, someone brought up an excellent question. What does the empirical mean in an empirical rate law? Because the content video that I gave you that was talking about this was titled Empirical Rate Laws. All that the word empirical means is by experiment. It means that we didn't assume what the form of the rate law was. We went in and figured out what the rate law was by running experiments. Now, the next week's material is going to go into a way to take a proposed reaction mechanism, as in and by mechanism I am meaning a series of steps by which the reaction occurs, and then determine what rate law that mechanism would predict for the reaction to go by. And what we will then do, and then the idea is you compare that predicted rate law from a mechanism to the experimental or empirical rate law, and if they are of the same form, if the equations look the same, then that rate law is consistent, is one way that that mechanism is one way that the reaction might happen. But if the rate law is different, then that means the mechanism is wrong. So the idea of using the word empirical here is to say we are determining it experimentally, either so that we can just predict what the concentration is going to be at a future time, or to try to get an idea of, try to compare it against proposed mechanisms to see which mechanisms might be true and which ones definitely are not. So that's the idea there. And then the question later is rate law versus reaction rate. So reaction rate is these derivatives. The reaction rate is deconcentration dt with whatever stoichiometric coefficient you have in front of it. The rate law is you take that rate and you have some kind of equation that says how this rate depends on concentrations. That's the difference between a rate and a rate law, so that you have an equation for it on this side. Okay. How are rate laws applied and what do their answers mean? Well, the main way they are applied is to plug in concentrations and then figure out how fast the reaction's going. So if you do that for a reaction like hydrogen gas plus oxygen, and you find that, wow, the reaction rate we're getting is going to be in the microsecond kind of time frame. If it's millions of reactions per second, or billions of reactions per second, that kind of thing, then you know that's going to be kind of an explosive reaction. It happens very quickly. If you plug in the numbers though and you find out that you're having a few molecules react every year, then you're talking geological timescales kinds of things. Or you can take the integrated rate laws and say, I'm starting with this much, how much will I have, how much product will I have at time X? That's useful for figuring out things like I have a reaction I want to do to make a product. Maybe I'm making a pharmaceutical for sale. You can then, the company can then say, I need to run this reaction for 3 hours, and then I get enough product that I can isolate it and use it and make the drugs that I need. That's the kind of thing that you do with it. So how do we use the rate law equations? So we're going to have some examples down here of doing that, so I will show that in a moment. How do you determine if it is, so the orders of reactions? So let's talk in general about forms of the rate laws. So there being a rate law generally just means there is some function of concentrations. And A, B, C, and so on, they could be reactants, they could be products, they could be things that are neither reactants or products. So they could be catalysts that would, where a catalyst is something that speeds up the reaction. They could be inhibitors, which are things that would slow down the reaction. And so a rate law in general, it just means that you have some function. Now, a very, very common form of the function is to have a rate coefficient that is multiplied by these concentrations raised to some powers. Not all rate laws are of this form, but enough of them are that it is probably the most important special case of them. These these powers do not necessarily correspond to the stoichiometric coefficients, except in one case that we'll be getting to next week. When we're talking about individual steps of a mechanism, there is a relationship there, but we haven't covered that yet. At the moment, we are just going to consider these to be experimentally determined exponents that we have. They are called the reaction order in the species, in species A, reaction order in species B, reaction order in species C, and the overall reaction order is simply the sum of the individual reaction orders. How do we determine those reaction orders experimentally? There are three main approaches that we have talked about for that. The first of them is called the method of initial rates. We went over some examples of this in class last week, and we went over, and I certainly went over an example of doing that in the very first of the rate law videos. I don't have specific questions on them on today's list of muddy points about the method of initial rates. So if we have time, we can do one at the end. If not, we can add it to the list and do an example tomorrow, which you could see on video if necessary. The second method for determining the reaction orders would be the method of flooding. And so we do have a question about the method of flooding that we'll get to in a little bit. And then the third method is only useful in the case where your rate law only has one species concentration that's involved. So the special case of single species, I can't spell today, all right. Special case of single species, you can plot concentration versus time, you can plot natural log of concentration versus time, and you can plot 1 over concentration versus time. If this one is a straight line, it is 0th order. If this one is a straight line, it is 1st order. If this one is a straight line, it is 2nd order. So that those are the three different ways we have for determining reaction order. Two of them are pretty general, but they involve being able to control, either measure the initial rate very precisely, or involve being able to run multiple experiments at different very high concentrations of some of the involved species for the method of flooding. And then you have one special case version where if you only have a single species changing, you can determine if it's first, second, or 0th, 1st, or 2nd order. Any questions on that, on determining reaction order? Okay. All right. How can we have a negative reaction order, and why does that imply the reaction gets slower at high concentrations? So the reaction orders, we've talked about the special cases of 0, 1, and 2. There are some cases where it gets up to about a 3. There are some cases when it is fractional, like 1/2, and there are some cases when it can be negative. Often -1 is the most common negative order you will see. The idea is that you will have your rate for negative order. It'll typically be positive in one species, but then negative in a second species. Okay, so I don't think you will ever find any rate that only depends on one concentration and it is negative in that, it has a negative order in that concentration. It is always something that happens, that occurs in conjunction with species that do cause it to increase in rate. So there are two ways to interpret this question. One is, what is it that about a negative rate that causes the rate to slow down mathematically? Remember what a negative exponent means. It means that this can be written as this. So a negative exponent means flip it into the denominator. And so the higher the concentration of B, the smaller the rate is. So just mathematically, this means that when you have B present, it slows down the reaction. Okay. Now, the second aspect is, what does this mean about the reaction? What's physically going on that is causing that to happen? And there are really two kinds of scenarios where that's the case. So imagine you have a reaction that is 2A goes to form B, a dimer. So this is dimerizing. The two molecules are coming together to dimerize. But then that dimer could break up and go back to A. So what that means is that if you have a lot of B present, but you don't have much A present, then the backwards reaction is going to be faster than the forwards reaction. And so what that's doing is making the rate of the forward reaction smaller because it's being counteracted by the reverse reaction. Another possibility for a negative reaction rate would be an inhibitor. So if you have some kind of reaction where A has to react with C in order to create our product D, but you also have another reaction that's happening simultaneously where C can react with B to form some other product you don't care about, E. So the more B you have here, the less of this reaction that's going to happen because it's getting rid of the C that you have that's available. That makes some sense? So in that kind of case, you could get a negative reaction order for B as well, because it's interfering with the reaction proceeding successfully. Okay. We also have a request for some example calculations, and I copied a few of them here. So I'm confident that is going to be smaller than anyone can see, so I will rewrite them. So one example here is a 0th order reaction with a rate constant K of 0.0416 molar per minute and an initial concentration of 2.29, I don't know why I'm putting that in brackets. So concentration of A initial equals 2.29 molar. And the question is, what will be the concentration of A at 20 minutes? Okay. So that's the example 0th order question we're looking at. So for this, you need to have the integrated rate law. So today, we haven't gone into that yet today, but we can look at that if anybody wants to. I am putting together an equation sheet for you that's going to be including these kinds of things on it. The 0th order rate law, the integrated rate law, is this. Okay. And so all we do now is plug in the numbers. So we have 2.29 goes in here. We have 0.0416 that goes in there. And we want to know it at 20 minutes, so that goes in here. So notice that if we take 20 minutes times 0.0416 molar per minute, we get a result that is in molar. So then we're subtracting that from the 2.29. So just calculating that out, we have 0.0416 times 20 gives us 0.832. So, and this is going to then be 2.29 molar minus 0.832 molar. So that's going to give us 1.46 molar will be the concentration 20 minutes in. Yes?
How does the KT give you molar?
The units on K are molar per minute. The units on T are minutes. So molar per minute times minutes gives you molar. Okay? All right. Everybody comfortable with this, this example? Excellent. There's another example here, which is kind of doing the same thing, just sort of backwards a bit. So this one is another 0th order. We have the reaction is 2NH3 goes to 3H2 plus N2. We have the rate constant for it is 1.50 times 10 to the negative 3 molar per second. We have the concentration of NH3 at T equals 5 seconds is 0.00402 molar, and asking for what was the initial concentration of the ammonia. Okay, so it's 0th order, so we have the same equation we did before, which is going to be NH3 concentration equals the initial NH3 concentration minus KT. We know this number, and this number, and so we're going to solve for the NH3 concentration here. All right. So, so I'm going to assume here that you are capable of taking the K, the ammonia concentration, and the time, and plug them in and do that. I have another example question that is looking at 2nd order reactions. So this one might actually be a little more legible than the other ones. So I'm not going to fully rewrite this one. Since it is a 2nd order reaction, our integrated rate law is different. So our integrated rate law, I usually remember it by the linearized form, just it's easier to remember how to write it. So the CH3CHO equals the initial CH3CHO concentration plus KT. All right, so we have a concentration at T equals 0, so that's going to be our initial. So here we plug in 0.551 molar. We have this concentration at T equals 3,600 seconds, so this becomes 0.523 molar at T equals 3,600, and it's asking for the rate constant K. So you have the numbers everywhere, and it is just algebra at that point to solve for K. Are we good with that? Yes, go ahead.
Can you do a first order?
Do a first order, sure. Let's suppose you're told that this is first order, okay? So I'm not gonna have to come up with random numbers. We'll go ahead and use the same numbers, okay? Let's assume that it's first order. So the form of the rate law for first order is concentration of your species equals the initial concentration times e to the negative kt. If you prefer to work with the linearized version, you can do that. That's the natural log of A equals the natural log of the initial concentration minus kt. Whichever one of those you prefer to work with is fine. It's just going to be a different kind of algebra that you're doing. In this case, we are plugging in exactly the same way as we did up here. We have 0.551 molar. So you take the natural log of that. In this case, we have 0.523 molar here. We have 3,600 seconds here. And so then you solve for K. So in this case, because you're trying to solve for K, it is probably easier to use this form than it is to use this form, just from an algebra standpoint. Okay. Does that make sense? Okay. All right. And the other example that came up on Piazza is very, very close to this example right here. So the the procedure is identical. Okay, here. So there was a conceptual question asked about integrated rate laws, about do you only do this for, do you use this equation only for radioactive isotopes, or is it just for a certain order? So most radioactive decay is first order. And so so first order, remember, rate equals rate coefficient times your concentration to the first power. So often the first power is left over. Or writing it in the integrated form, or the linearized form. I guess I'll put it up here. All three of those are equivalent to each other. It just depends on what which one's easier to use in your given question. These equations are true for any first order reaction. Most radioactive decays are first order reactions. So fission is first order. Radioactive fusion is typically second order, but fission is first order. So generally, this is you'll get some practice with this on the next group activity, because we're going to be looking specifically at radioactive decay, and we're going to be applying it to the question of how do we experimentally know the age of the Earth to be 4.5, 4.6 billion years old. And it comes down to being able to understand the kinetics of radioactive decay of components that are in minerals. Okay. Half-order reactions, what do they look like when they're plotted, and what would their axes be? So I'm assuming that this question is asking about sort of the linearized versions, where I was saying somewhere here that for 0th, 1st, and 2nd order, that there are ways you can plot it, and if it's a straight line, you know it's 1st order, or in this case, 0th order, 2nd order in those cases. For half-order reactions and negative order reactions, we have not gone through that process to determine what a linearized version would be. You could certainly do so, but they are uncommon enough that people don't tend to have that as one of the things that they have memorized to work with. So, and I'm not going to be asking you to determine them by that method in this class. There probably are some formulas for it, but I've not even gone through them myself to determine what they would look like. What you can do, though, is use the method of flooding or the method of initial rates to determine that if it's a fractional order or a 0th order, excuse me, a negative order. The method of initial rates in particular will give you that information directly, very easily. So, so that would be the only context within this class where you would have a result that would show up as a negative order or a 1/2 order. Any questions on that? Okay, method of flooding, what is it for? Okay, so I'm going to do a, how are we doing on time? We started 10:30, okay, we got some time. So, method of flooding. The idea of the method of flooding is, let's imagine we have a rate law that can depend on multiple things. My black is dying. Let's switch to blue. And we want to know what the rate law is. We suspect it is of this form. And so determining the rate law comes down to determining A, B, and C for the reaction orders and the rate coefficient K. Once we have each of those numbers, we then say we know the rate law. So what do we do for the method of flooding? What we do is we take two of these species and we make their initial concentrations huge compared to the other one. So if we have our initial concentration of A be 0.001 molar, our initial concentration of B is 1.000 molar, and our initial concentration of C is also 1.000 molar, then when the reaction is done, let's suppose we also know the reaction stoichiometry so that it's A plus B plus C goes to products. So we have ones in front of all of those. Then once the reaction is completely done and all of the A has reacted away, because it's the limiting reagent, do you remember limiting reagents from last semester? So our final concentration of A is going to be 0. But what's our final concentration of B going to be? For every molecule of A that reacts away, 1 molecule of B reacts away. 0.999, exactly, 0.999 molar. Concentration of C, final, is also 0.999 molar. Now, how different is the initial concentration from the final concentration here for B and C? They're the same within 0.1%, right? Very, very, very close to the same value. So what that means is that if we set up our initial concentrations like this, then over the course of the entire reaction, as it's reacting away, well, this is obviously a constant, but these are effectively constants as well, because the concentration of B and the concentration of C don't change over the course of this particular reaction with this set of initial conditions. So let's fold those together into something we're going to call K observed, which is going to be K times our initial concentration of B to the B power, and our initial concentration of C to the C power. And then we can rewrite our rate as this K observed times the concentration of A to the A power. What we have now done is we have taken this reaction and taken it from something that's really complicated, that has three concentrations changing at the same time. I mean, the calculus involved in trying to find an integrated rate law for something like this would be crazy, absolutely nuts. But here, by setting up our initial conditions in a way that we can treat two of these as constant for this, the specific conditions we're doing it under, we've reduced it to a case where there's only a single component that is changing. So at that point, we can do this. Plot concentration versus time, plot log of concentration versus time, and plot 1 over concentration versus time, and see is it first, second, or third order, or 0 first or second order. I keep saying third. Let's suppose that in this particular example, that when we plot natural log of concentration versus time, we get our straight line. That one experiment then tells us that A, even the A up here, because it's the same A, equals 1, because we now see that the correct plot is a straight line for it to be first order. But also it tells us, so if we go back to our linearized version of this, of the first order equation, we see that the slope is negative K. In this case, that's this, our K observed. So slope equals negative K observed. What that lets us do now is do this experiment again, but maybe flood it with a different amount of B. Maybe we use 2 molar. Maybe we use 1.5 molar. And looking at this equation right here for K observed, we can see that B, changing B initial, while still flooding, just flooding with a different amount, is going to change our K observed, which we get from this. So we can take that slope, that K observed, and we can plot K observed versus our concentration of B. Let's suppose we do that, and we get this. It's a straight line that goes through 0. What does that mean our exponent B has to be, lowercase b, if this is a straight line? Saying 2? 0? If it were 0, then if this were 0, anything to the 0 is 1. This would not be in here at all, and changing B would not change the K observed. So it's not going to be 0. Good first guess. Yes? 3. So if this were a 3 for B, then if we double the concentration, we take 2 to the 3rd power, which would be 8, our rate would go, our K observed would go up by a factor of 8. If we double it, it would go up by a factor of 8, and we would see something that looks like that. So we get a curve that goes up like that. What is the functional form for a straight line? What's the power of x in y equals mx plus b? 1. Linear means the power of 1. The power is 1. So in our example case here, seeing that K observed versus concentration of B is a straight line tells us that B equals 1 as well. Now let's do another set of experiments where we hold the B constant and we now change our flooding amount of C. So we do that, K observed, not O, C, do this, and let's suppose then we start to see something that curves. Well, so it's not linear, it's something bigger than linear. So you start trying things. Well, if it's second order, then if we plot square root of K observed versus concentration of C, the square root would give us a straight line. And then that would tell us that C is 2. So the method of flooding is a way to take a complicated proposed rate law and break it down into components so you can individually determine the reaction orders very easily. Well, I say very easily. You probably have to run like 10 or 15 experiments to do it because each one of these dots is a separate experiment that's being performed, right? Okay. Any questions on method of flooding? Yes?
So in this problem, K is 1, B is 1, and C is 2. Does that mean that the overall order would be 4?
Yes, it does. The overall reaction order would be 4 in this example, absolutely. Yes?
Could you just explain how you got from the K observed to the R equals K observed A one more time?
Yes, sure. So the question is, can I explain how we got from here to here? Okay, so the idea was we looked at the initial full rate law that we're trying to figure out. We took all of the parts that are multiplied together that are going to be constant within a given set of initial conditions, and we multiply them together. So this is constant, this is constant, this is constant. So we combine them into this thing we're calling K observed. Now we look up here and say, how can we rewrite this plugging in K observed? If K observed is this thing, and this thing, then for the full rate law, all that's left to be multiplied by is A to the A. So that's where the A to the A comes in here. Okay. All right, so that is method of flooding. The next questions we have are on half-lives. I'm going to go to the next page here. Where do the equations come from? Yes, let's do that first for the for first order, because first order is the rate law where half-lives make the most sense to use. So let's start with talking about that one. Let's remember that our rate law for first order, A is A naught times e to the minus kt, or if we want the linearized version of that, then it is natural log of A equals natural log of A naught minus kt. So the idea of a half-life is a half-life we label T1 half. It is the time it takes, the time at which the concentration equals half of its initial concentration. Okay. So what we are going to do is plug these two things into this equation here. So this is the definition of a half-life, and that's true for any order. This definition, it's the time at which the concentration is half of the initial concentration. We are now going to plug these two into the specific case of the first order rate law. So we're going to plug this in for this. So we have natural log of concentration of A naught over 2. Right, equals natural log of concentration of A, initial, minus K T1 half. Okay. So all that was plugging in. Everybody with me to that point? Okay, so I'm going to rearrange slightly. So I'm going to do K T1 half equals natural log of A naught minus natural log A naught over 2. Okay. Everybody with me at that point? Just move this to the left, move that to the right. Now, when we have natural log of something minus natural log of something, we have, so natural log of x minus natural log of y equals the natural log of x over y. That's a fundamental property of logarithms. So that means that our kt to the 1/2 equals the natural log of a naught over natural log of a naught over 2. Right? Well, natural log of a naught over a naught there cancels, so we end up with 1 over 1 over 2, which equals the natural log of 2. Let's remember, this is k t 1/2 equals natural log of 2. So t 1/2, our half-life, equals the natural log of 2 over the rate coefficient. So that is where the half-life value comes from. And the utility of the half-life is that it makes more intuitive sense to talk about than the rate constant does. So if I told you that the rate constant was 10 to the 6th per second, what's that mean? But if instead I tell you it has a half-life of a microsecond, that immediately tells you in a microsecond, half of it's gone. So in a second, there's going to be almost nothing left, right? So the half-life idea makes a lot more intuitive sense and is easier to think about its meaning than the rate constant by itself is. But they contain the same information for a first-order reaction. Now, the problem is that while you can go through this same analysis for a different rate law, for second order or 0th order or something like this, you can come up with what's the half-life. But this one for first order was convenient because the initial concentration canceled, and the half-life doesn't depend on how much you started with. It's just a number. But that is not true for second order, and it's not true for 0th order. First order is the only case where it cancels out and where the concentration cancels out, and the half-life is a property of the reaction, not of how much you start with. So so you can go through and calculate what the half-life formula is in the other cases, but from a practical standpoint, it's almost useless. It's much better to talk about the rate coefficient in the second order case and in the 0th order case. Does that make some sense? Any clarifying questions on half-lives? Okay, so I think we have about 5 minutes left. Let's see. Okay. So where do the equations come from? We just did that. This is half-lives. Why are they constant for first order? I just went through that. And increasing for second order and decreasing for 0th order. It's just a question of the concentration not canceling out when you go through that same analysis. That's all it is. And I wouldn't spend too much more time thinking about that too much because nobody uses them in the context of second order or 0th order. All right, somebody asked about bimolecular reactions. What are they and how do you determine if a reaction is one? My answer to that is wait till next week because that is part of the reaction mechanisms and collision theory kinds of stuff that we're going to be going into there. The fact that this came up already makes me wonder if there were any Newton questions about it already. Has anybody run into a Newton question about a bimolecular reaction yet? No? Okay, good. Because we will be covering that next week. Okay, that was everything I had on kinetics. So there were a few other miscellaneous questions, in some cases relating to some stuff from the exam I want to go through relatively quickly. Does the presence of a hydrogen bond automatically guarantee that there will be a dipole-dipole interaction? The student answer in this case said yes, but that's actually not true. So, for example, if you look at the example from the exam of CF4. And this is you have this in a system where there is some kind of hydrogen bond donor somewhere. Well, this over here is going to have a dipole moment. This here does not have a dipole moment, but yet you can have a hydrogen bond with it. So there's not a necessary connection between hydrogen bonding and polarity. It is common that it will be because the hydrogen bond donor is going to have some polarity, but the hydrogen bond acceptor does not have to have polarity. Okay. All right. Does molar mass change when an atom is an ion? That's an excellent question. So can somebody tell me what's the difference between a fluorine atom and a fluoride ion? Yes? The ion is charged, and so what has changed to the fluoride, what has changed to the fluorine atom to make it a fluoride ion? Number of electrons. So has it gained or lost electrons? Well, you should be able to tell that by looking at the periodic table. It is in group 7, right next to the noble gases, yes? It gained 1 electron. So it has a charge of -1, so it has gained 1 electron. What is the, how many protons and neutrons does a fluorine atom have? Not individually, total. It has a molar mass of about 19. So that means it has 19 protons or neutrons. What is the mass of an electron compared to the mass of a proton? Almost 0, but yeah, I think if I'm remembering correctly, a proton or a neutron is something like 1,900 times as massive as an electron is. I may be off on that number, so don't quote me. So what that means is that if you take 19 of those protons as the mass of the atom, and you add an electron to it, it is effectively unchanged mass. So ions have the same mass as the neutral atoms, unless you go out to a stupid number of significant digits. Okay, all right. And that is about all we have time for right now. So thank you very much. Any questions I didn't get to, take a look at the recorded class section timestamp for the class that you're not assigned to go to, and you should be able to get to those questions specifically later. Thank you all.